welcome everybody. Welcome back.
You can see the PPT.
I can see the PPT.
Yep, your PPT is fine. Our talk today is about
you need to put it on full screen though, Trevor.
Optimizing approaches to training an autorater engine for the assessment of constructed response speaking tasks. I'm Marvin Wall. I'm a language assessment consultant for the British Council, and I'll be your host for this session. With me is my colleague Chris Horn, and he'll be in the background. Please, a reminder, keep your microphones muted, and we'll also be recording this presentation and uploading it to our lobby platform later today. Please feel free to ask our presenters questions in a chat box, and our presenters will address them at the end of their presentation. So about our presenters, first we have Trevor Breakspear. Trevor has 18 years of teaching and training experience within the Chinese ESL and EAP context, and over 10 years of project management experience in assessment and localization fields. Trevor works in an innovations role within the British Council's East Asia Assessment Solutions team, currently leading on the academic development of new AI scoring assessment tools, as well as coordinating and presenting academic and stakeholder research into new test concepts, leveraging both AI and human raters. Our second presenter is Jan Langeslaag. Jan has 13 years of experience in the EFL field, both as a teacher and assessment expert. In his current position as an assessment solutions consultant with the British Council, Jan works to promote language assessment literacy among teachers, students, and other test stakeholders throughout Southeast Asia, and is involved in validation research for new assessment products. And finally, we have William Bayliss. William has worked in the field of language teaching and assessments for years. He worked as a teacher and an academic manager in Chinese private language schools before transitioning into the role of an assessor, assessment trainer, and now consultant. So with that, I would like to hand over to the group for today's presentation. Over to you.
Thank you very much, Marvin, and thank you all for taking time out from your busy weekends. So one thing that I've been very impressed about with the conference so far is the sort of the focus on the fact that with technology, we need to take a more multidisciplinary approach. So we need to combine expertise and work together in order for this technology to be most appropriate for our learners. Today, we're sort of talking about that. So we're thinking about how, as test developers, we can work with tech suppliers in order to enhance and build speaking assessments for a variety of stakeholders. In today's presentation, hopefully I can present, and along with my two colleagues, William and Jan, some insights on what we can do to provide data for AI scoring, how we can have a positive influence on this process, and also to admit and to discuss some of the challenges that we face going forwards. So before we look at the actual machine training, I want to quickly overview the assessment tool. The product that we are looking at developing, and we have already started to develop, is IELTS Smart Learning. It's owned by the IELTS partners, that's British Council, Cambridge Assessments, and IDP. It is a low-stakes AI-rated speaking solution. It's based in the Chinese market for ages primarily 12 to 16, covering a CFR range of A1 to B2. The first interaction that a student will have with this product is a placement test, and this is designed primarily to position them within the product at the right level, so they're not wasting time with materials that are too hard or too easy. This placement test, in order to do so, does tap into more constrained tasks. For example, you can see at the top, what time is it? Would be a very much A1, very constrained task. When we go up towards the B1, B2, though, we're asking questions such as, well, what did you do on your last holiday? And for example, comparing a long holiday and the merits of a short holiday. So they're much more open response, broader construct tests, and tapping into functions including descriptive, narrative, and argumentative. These are not easy for machines to rate. So it's challenging, and it's something that we want to assess the machine on to see how well they can do. The placement test is holistically scored, and as you can see, it provides a recommended star point within the product between 1 and 12. Now, the product is designed to be used over time to give practice opportunities for speaking and to therefore allow stakeholders, including users and teachers, the opportunity to map and assess their own progress. So what have we been doing then? Before we even started this, we needed to tap into what we call the target language use domain, which is basically what the Chinese students in our context are actually doing with spoken language. What tasks are they using in the classroom? How are they being assessed? How is it positioned in the curriculum? And what skills are being targeted? I mean, is it phonology? Is it fluency? Task completion? So after doing this, primarily desk research and also some interaction with our stakeholders, we had to develop the specifications based on this. And for us specifically, these are the specifications for the questions, the prompts for speaking, but also the rubrics or the band descriptors that the raters use in order to make decisions on the scoring. Once we have that in place, we can start training. So we're training the raters on the use of the rubrics, the band descriptors. We go into looking at data management, QA, to ensure that the human raters are rating consistently. We then provide data to our tech supplier. Within that process, we're optimizing data, we're receiving data back from the machines that are being trained, and we're comparing human and machine scoring and those correlations. Now, as you can see from the diagram, this is an iterative process. So we do this, we get the data back, we look at our data, we retrain, we put more data into the system, and we continue in this cycle. So I wanted to talk briefly about the scale design and rating principles. First of all, we used a set group of 6 raters. They're the same people over 6 months it took to do this. And we divided them into 2 groups of 3. Each sample was rated by at least 3 raters and sometimes 6. This could be considered overkill really for a low stakes context. Even in high stakes assessments, it's usually 1 rater, perhaps with a 2nd rater if there's an anomaly. But in our test, we are using 3 raters, if not more, and we're providing feedback on a weekly basis, which is incredibly high frequency. So why are we so interested in quality? Well, the answer is if you're developing a auto rating test, then the consequences and the impact is incredibly high. You can scale that so that this same model, based on this data, can rate thousands, tens of thousands of students across China, a massive country, a big range of schools and different cities. So we obviously want to ensure that the data going in is as good as possible so that the data going out and being used in the scoring is as good and appropriate as possible for our test takers. Very briefly then, so we have a 7-band scale from A0 to B2. We're targeting, as we've said before, quite open tasks and so fairly broad construct. We're looking at task engagement, so engaging relevantly with aspects of the prompt. We're looking at fluency, so thinking about hesitation and searching for lexis, and this is at band 4 here. Lexicogrammar, so simple vocabulary, but maybe a mix of simple and complex forms. In terms of pronunciation, intelligible with occasional lapses. This is a sample descriptor at band 4. That's kind of the beginning of the B1 band. So for the rest of this presentation, we want to explain how we've captured that data and how we're sharing that and working with our tech partner to develop the models. Will be discussing the data management of that process, how we're representing data, how we're using that to train our raters, and the impact of that on the human-machine correlation. He'll talk about that briefly. Jan will then go on to talk about how we're optimizing that data to ensure that what we're providing is the best possible quality. So if I can hand over to you, Will.
Thanks very much, Trevor, and good afternoon, everyone. In the next few slides, I will talk you through our strategy that leveraged previous iterations of the machine rater to populate training data at the extremes of the test rating scale. Well, why would we want to do that? I'll give you a bit of background. As Trevor pointed out, the machine is only as good as the data that we train it on. If there isn't enough data in parts of the scale, reliability will suffer. Good training data requires a flat-ish distribution across the scale. The ratings from the project tended to fall into a rough normal distribution. It was also common for raters to rate normatively, that is to lean towards the middle bands of the scale. The result of this was that there wasn't enough data at the extremes to train the engine. The machine training data was composed of human rater scores from 13 batches of samples rated by 3 groups of raters. The first 10 batches of samples were randomly assigned. That is, we just got the data and gave it to whichever rater was available. The final 3 batches used were filtered using the machine trained on the data from the first 10 batches. I will explain how we went about this in due course. Could you put the next slide on, please, Trevor? Here are the histograms from batches 8 to 10 for both of the rating groups. As you can see, the data is concentrated in the middle bands. This is possibly due to the nature of the sample and possibly due to normative rating. Batch 8, group 2, is an outlier. I investigated the data and found that one of the raters was rating very leniently, which accounts for the histogram's skewed distribution. Next slide, please. The machine rater was trained on the data from the first 10 batches. This slide shows the human-machine comparison correlation, which scored 0.8. We can clearly see that the outliers tend to fall at the extremes, most notably at the high end. Possible causes of these outliers were limited data at extremes and, again, normative rating. Our aim was to address these issues to see if it would affect the performance of the machine. The key issue at this point was the cost of further batches. We had a limited number of further batches and we had lots of data. There was no guarantee that these further batches would give us the data that we needed. We wanted, therefore, to make sure that the data we chose for the final 3 batches covered the range of scores we needed and was rated as effectively as possible. The machine had become very proficient at selecting bands 3 and 4. So why not leverage this? We had the machine rate all of the remaining samples and then used the scores to limit the number of those band 3 and 4 samples. To make the rating as effective as possible, because it was very expensive and hard to get the data, we wanted to make sure that the raters rated it as well as they could. To do this, we created a standardization batch made up of samples chosen from previously rated samples. I purposefully chose samples rated earlier at the high and low bands. This allowed us to highlight and address normative rating. Myself, Jan and Trevor rated these samples, wrote profiles for them, and then compared and agreed scores. The raters were then asked to rate the samples and write profiles for them. Next slide, please. Here you can see 2 histograms that represent the standardized scores on the left, that is mine, Trevor and Jan's scores, and the initial human rater scores from the batch. As we feared, there was a tendency for the raters to drift towards the middle bands. Profiles and scores that were a poor fit had to be rewritten by the raters. If after the second batch, the ratings were still a poor fit, we followed up with raters and guided them towards the standardized score. Next slide, please. The raters were given 3 final batches to rate. As you can see from these histograms, the distribution of human scores was much flatter, giving the machine more data to train with at the extremes, which is what we wanted. So we were very pleased. Next slide, please. After training, the machine was compared with human raters again. As you can see from the slide, the new data had a huge impact. First, the human-machine comparison correlation improved by more than 0.1. Also, the scores are much more evenly spread, and there are fewer outliers with clear achievement of scores across the bands. It needs to be clearly stated that we're not claiming our intervention improved the machine's performance per se. What we did was provide it with the data it needed so that it could perform at its best. Now over to Jan, who will discuss the training data in more detail.
Right, so with whatever time remains, I will walk you through the machine input, which is what we actually fed into the machine at the end of the whole process. We used what is called a fair average. I will very briefly explain the concept of this. As mentioned before, each response was rated 3 times individually by 3 well-trained raters. A lot of work has already been done on training, standardizing these raters with feedback and so on. So even if we just took the mean score of these 3 raters, that would count as, a fairly reliable measurement already. We added another step, however. We took the observed average, which is simply the mathematical mean of the 3 raters, and then used multifaceted rash measurement using the program Facets to slightly adjust these observed averages, taking into for the raters, the different severity. With that, we arrived at a fair average. Next slide, please. Next, yes. Here are the facets that we used in the rash analysis. The 2 facets here on the left, candidate ability, which is what we are seeking to capture, and rater severity, the influence of which we are seeking to minimize. It would make sense, of course, to also include a prompt facet. However, we decided not to do this. The 3 prompts actually represent very different constructs that we're targeting. As Trevor explained, we've got description, narration, and argumentation. It would make sense to include this if we were seeking to establish the relative difficulty of each, but since we are seeking to isolate the performances on each of these prompts separately, it would make more sense just to leave it out. So in the end, we went with a bare bones 2-facet model. Next one, please. Here, you see a quick overview of the scoring proximity by the raters. We see that 67.1% scored within 0.05 bands of the fair average, while 95.6 scored within a whole band. It's important to keep in mind here that this data is taken from the uncleaned, from the raw scores that were provided. The actual fair averages, however, they were established only after cleaning the data by removing the outlying responses. If we can go to the next slide real quick, please. Here, I'll walk you through very quickly through how we went about the data cleaning. For this, we used a table from the rash output file for the unexpected responses. You will see a simplified version of this on the left. You will see a candidate number on the very left, and then towards the right, a score that was provided, a score that was expected by the machine based on both the other raters and the relative severity of this particular rater. The residual to the right is the absolute difference between the observed and the expected score. Wherever the residual was higher than 1 band, we see that the score is a little bit suspect, so these will have been removed. However, if there was 2 scores on the same candidate that both had 1.5 residual, we usually exclude the entire response from the analysis. This happens, for example, if we have 3 raters scoring a 1, a 3, and a 5. Of course, we could say that's an average of 3, but if they score all over the shop like this, we can say we cannot have very much confidence in the rated decision here. That's why some of these responses, or they were removed. It's a small number of total responses, however. Okay, if we can go to the last slide. If there's still time, there is. So what does this mean for scoring validity of our product? It means we have an extra safeguard against influence of rater severity on scoring variance. There's already a lot of safeguards against this: rater training, optimization of performance through feedback and monitoring and so on, as Will told you about. But this is just one extra step on top of that. Thank you very much. That's it from my bit.
Thank you,
Jan.
Thank you, Jan.
Sorry, Marvin, I've just got one slide to do. I'll be very, very quick. So as Jan and Will have been talking about data, and really it sounds like then that we're just using correlations and statistics to say that machines are rating in the way they should be. So does that mean, for example, that a good correlation is what we call a good construct alignment? And the answer is no. And what I mean by that, can we be sure that the machine and the human are rating the same thing? And the answer is we can't. One of the big challenges we have now is to try to align exactly what is being measured with within the machine there. We could almost say the brain is like a black box as well, aligning those two. That is a very important piece of research that we need to start doing. And by doing that, we can give more confidence to our stakeholders to say, actually, this isn't just about numbers. This is what we're measuring across machine and human, and it's applicable to our users. Will also talked about the importance of more data. We bring more data in, we retrain, we have better representation of proficiency. And we saw that increase in terms of correlation. But also we're also incorporating features from a wider range of test takers, which is really important because obviously our model should incorporate as many possible approaches to the same response as possible. And finally, outlier analysis. Actually, Jan did talk about this in terms of removing outliers, but we also want to look at why some outliers exist. And basically this means, for example, there are some people who answer a prompt in a very unique way. We must make sure the machine does not punish them for being creative. And creativity is often the enemy of predictability. If your machine is based on predictability, then we need to address that and make sure we're being fair to everyone. My final point is really about validity. And we've seen traditionally that we do validity and then we finish at the end, we finish the test, our work is done. This is not how it should work with AI development. We develop iteratively, we therefore validate iteratively. We keep going in cyclic steps so that we ensure that we get more data and it's more applicable to our users. So that's the end of our presentation. I hope you see that we can, as test developers, get involved in the training of auto-rated technology without having to be experts in the field, but also that we've a long way to go and it's an exciting journey. Thank you very much.
Thank you, Trevor. And now let's go to the Q&A session. We have a question from Steve Adams. Steve asks, if the correlation is high, does it matter whether the construct aligns? Is this an academic conundrum rather than a practical consideration for test designers?
I'll take that question. It's a great question. Is that people try to game systems. So for example, there's often, particularly in higher stakes context, the feeling that, okay, we've got a computer, we know what they can measure, so we will give them what they want. Good examples would be, for some high stakes tests, if you speak faster or you use a few fillers, then you can get higher scores. And the point is, normally the correlation wouldn't reflect that. But if you do something different, then that correlation will be affected by, as I mentioned briefly, outliers, unpredictable performance. So yes, as soon as you put the machine under the spotlight, you start to see the cracks, particularly with unconventional responses and gamification. So we certainly want to start aligning and being able to demonstrate that we do more than just present that correlation, that we've accounted for these variabilities. And also by doing that, we're more responsible in terms of washback as well. We're saying that we're not encouraging test takers to try and beat our machine. We just want them to learn to speak English better.
So if anybody has any more questions, they could put it in the chat box. Okay, we have a question from Iris. How are you going to use feedback to enhance rater consistency?
I can take this one if you like. Rash analysis is fantastically useful for giving the raters feedback because, as Trevor said, we analysed every single data point that we looked at and we reviewed them weekly, which meant that when we had these outliers, we could look at the outliers and we could find out what was happening with that outlier. And it was interesting because you have 3 raters and maybe you do have like, I don't know, say 2 2s and 1 6, but then you would listen to the recording and then you would find that you actually agreed with the 6 and not the 2s. So it wasn't the majority of raters that you agreed with. But the really useful thing about that is then you could talk to those 2 raters that gave those 2s and you could ask them why they gave those 2s and ask them to write profiles for it, which allowed us to constantly feed back to the raters when they were straying path, as it were, which meant talking to your question that we were able to massively enhance.
We have a question from Marilla. She asks, would this help students perform better on the IELTS speaking test, or is that a different task?
This one is a very big question. What we've described in today's presentation is a process to auto-score a placement test that then gives you a level within a product, which does include IELTS type tasks. And the answer is those IELTS type tasks certainly can help prepare learners for the IELTS speaking test in a variety of ways. Some of them are obvious. So for example, we're providing regular opportunities to familiarize learners with the task types. They're receiving feedback on their performance, particularly in areas which are easy for the machine to consider. So this would be things like phoneme accuracy issues for pronunciation, issues with grammar, vocabulary, these kind of issues. However, what we're doing, which is quite exciting, and I think I can mention this, it's sort of in the R&D phase at the moment, but we're looking at using technology to actually simulate some of the functions of examiners in part 3. And I want to say absolutely categorically, we are not replacing examiners. This is not going to replace IELTS. This is very much a practice test. It's a low stakes context. But why is it exciting? Because if you want to, get an IELTS examiner to practice with you, well, that's virtually impossible and very expensive. But if we can get a machine that can imitate some of those functions, particularly, and this is one thing that's very exciting, is that when you say something in a part 3, the trick is that the examiner will then ask a question to make you follow up on that and to expand on what you've said. So for example, it could be, you could say, I don't know, it's important that we protect this area from too many tourists. And the examiner would say, can you give me a reason why? Does everyone agree with that? These are these follow-up questions. And we're starting to develop tasks using AI tech that can actually tap into these constructs. It's quite new, it's quite exciting, and I think learners will benefit from it.
Okay, thank you, Trevor. I'm afraid our time has come to an end. Thank you very much, gentlemen, for your presentation. And thank you all for being here. We hope you found this session informative. Just to remind you, the next session will be about evaluating automatic voice recognizers for rating non-native, open-ended spoken response. Hope to see you then. Bye.